F, right? You don't need to memorize, but I really want you to go through the process. First, go through the process with me in the class, and then in the homework, you will go through again because I shared the textbook, the chapter already, chapter 9. You can go through it again. And in the assignment, you need to do it for the direction in the Y direction instead of X direction. So these are the 3 times that you will get used to it, right? And I'm not going to ask you to derive something like this in your exam, so don't worry about that. But I may take a step and ask you to find out what is the element of the Hamiltonian, right? If I want, those are some simple things that you should know. So let's review what was the experimental setup. So the experimental setup is in the real 3D space. I have a DC magnetic field pointing down, so it's negative Z direction. Okay, so B0 is positive, so I put negative B0 means the magnetic field is pointing down, right? And at the same time, I have a small oscillating magnetic field B1 cosine omega 1 X hat, oscillating in this horizontal direction, right? In the homework, I asked you to change it to oscillating in the Y direction, okay? So you're oscillating in the X direction. Then the first thing we need to set up is to understand what is the total magnetic field. And it is easy, of course, it's the X direction plus component times X hat plus the Z direction, right? What's the value in the Y direction in this case? 0, right? And that's why I can write it as a vector. This is a real 3D vector, right? This is the X component, B1 cosine omega T, and this is the Z component, and Y component is 0, right? This is a regular magnetic field that you have learned in electromagnetism in any other classes, okay? But what we really, we learned earlier is that for the Hamiltonian, right? For the Hamiltonian of this system, if I have a spin, an electron with spin, now we only talk about electron. The Hamiltonian means the energy due to the presence of magnetic field. We know that is equal to gamma, which is the gyromagnetic ratio. This is something you want to put in your cheat sheet, right? Because I don't ask you to memorize it, but you should know what is gyromagnetic ratio, right? It's the inner product, right, between the spin angular momentum operator and the magnetic vector, magnetic field vector, right? The gyromagnetic ratio is GE divided by 2m. Again, for G, for electron, is -2, about -2, right? So I can just cancel that. Okay, but because G is -2, so negative times -2 becomes positive, right? So that's why here I only have E divided by H bar. And I hope you remember what is the spin angular momentum operator, right? The spin angular momentum operator, you can refer to your previous note, but basically it is just equal to H bar divided by 2 times the Pauli vector. H bar divided by 2 is easy to memorize because we have learned that if you the spin up is plus H bar divided by 2 for the angular momentum, right? And it is negative H bar by 2, right, for spin down. Depends on the magnetic field, plus minus. And then all you need to do just add this Pauli vector, right? What is Pauli vector? Do you remember? Thank you. So in the column vector is sigma x, sigma y, sigma z, right? And if you want to spell, it's sigma x, x hat plus sigma y, y hat plus sigma z, z hat. So yeah, it would be good to memorize, I think, right? So this is just a dot product, then it's easy, right? This is the magnetic field I put in the row. And this is the Pauli vector I put in column. I do the dot product, right? And then we went through all the simplification, eventually we say this Hamiltonian, which describes going to control the action of this system, is composed of one is H0, the major Hamiltonian, and then HI. Here I call it HI. It's more a perturbation Hamiltonian. It is a small one because this H0 is negative B0 H bar E divided by 2m sigma Z. Right? I cannot memorize this. So maybe better people can do that, but you don't need to memorize. But the point is, this is due to the vertical DC magnetic field. It creates this amount of energy. But then this oscillating horizontal magnetic field creates this HI, which depends on B1 and cosine omega 1t, right? So here we assume B1 is much smaller than B0. So it's a perturbation, a very small perturbation to the system. So then we can use the so-called perturbation theory. Any question about this? Again, never attempt to memorize this equation, unless you're very interested in that. That is great, right? If you have insight, you will be able to memorize it, right? It took me a long time, right? But if you cannot, don't worry. The point is you understand how to derive. Although I already said that I'm not going to ask you to derive from basics, the whole thing, right? But it will be good to write intuition on how to come up with the whole thing. Set up a magnetic field, find the Hamiltonian, solve the Schrödinger equation, and then what, right? 4 steps, write it down. It's a good exercise, okay? So, we already written the Hamiltonian, then now we need to solve the Schrödinger equation. But what we're trying to say is that there's something called perturbation theory. Before we apply H1, where you only have the magnetic field pointing down, we already know that from experiment or from previous exercise, there are 2 possible energy outcomes. One is mu B, B0 mu B is the Bohr magneton, right? Or it can be written as negative H bar omega L divided by 2. This is omega L. Sorry for my writing, right? But again, this omega L. Do you remember what is the name for omega L? L is called the Lamarck frequency. That is the frequency the qubit will process about the z-axis. So this is a characteristic frequency of that qubit under that electric field. And it determines the splitting, right? The difference between level 0 and level 1. So if you feel aliens about this block, then it means you need to go back to study again about this Lamarck precession and try to link them together, right? Before we apply the magnetic field, spin up, spin down have the same energy. They are so-called degenerated, same energy, different state. We apply the magnetic field, then one of them, spin up has a lower energy, spin down has a higher energy. They got split, right? And the splitting is due to this, what is called Zeeman splitting. They have this energy. And again, I keep emphasizing, when you do measurement, you will get some real number. This number corresponds to the eigenvalues of a certain operator, right? And that operator is actually this one times sigma z. Okay? Okay, but let's just ignore this for now if this is difficult to catch up. The point is, do you agree that under the external magnetic field, it has 2 energies? Right? One is E0, one is E1. We derived it before, but you can check again. But we agreed that it has 2 energy due to splitting. And then the perturbation theory tells us that, okay, then if you add a new extra perturbating Hamiltonian, the solution, the wave function, is still a linear combination of the original basis state. Okay, except that now the coefficient is given by these 2. Of course, yeah, Because if you go to a new system, really different system, your basis state might change, right? But now it's only a perturbation. You still have it at this basis state. But then all you need to find is to find out the coefficient. Is that okay? Okay, so then that is what we are trying to do, right? So because of this, then we plug in, we again write down the Schrodinger equation. This is where we stopped from last time. IH bar partial psi partial t equals to the total Hamiltonian times the wave function. Okay, but I substitute it by H0 and HI because the total energy is H0 plus HI, right? So now I'm going to plug in the wave function. We say this is the wave function when I add HI, right? So all I need to do is just plug in. So this is negative IH bar times this, the derivative of this wave function, right? So the derivative of this wave function means I need to do partial this guy, partial t. So first of all, I will try to do derivative on the first term. But first term is the product of two time dependent one, right? C0 is time dependent. It's not a constant. And that's why I put C0 dot. And then multiply this one. And then plus, now this time I do C0, but then do derivative on e to the power I omega 2, right? So I will take out this exponent, become I omega L divided by 2, and then times it. What I'm doing is just this rule. Partial differentiation of A times B is just A dot, the time derivative of A times B plus A times the time derivative of B, right? I'm just use this rule. So that is what I'm doing. Is this clear? Any question? You need to make sure you understand what I'm doing. I know a lot of things can be very confusing. If you understand this, the rest will be just straightforward. Any questions about what I'm writing here? Last time some people told me that they cannot see the dot, which is the partial C0 partial t, right? So make sure you understand. So this term is okay? Okay, then I further do the derivative on the second term, right? So I do the same thing. C1 dot means dC1 dt, right? So maybe I should just be very clear, right? C0 dot means partial C0 partial t, right? C1 dot means partial C1 partial t, okay? Then there will be no confusion. So I do the same thing. I first do time derivative for C1, I keep the rest. Then I keep C1, I do the derivative for e to the power negative I omega t divided by 2. Then of course I need to take this out, right? Because just in case you forgot also, d e to the power at dt is just equal to a times e to the power at, if you forgot. Okay, that is what I'm doing here. Is that clear? Right, you need to do this for your homework, right? But basically you just copy. So that's the left-hand side, right? I expand it. Then the right-hand side is what? I will just multiply H0 plus I to this whole term, but I try to separate it to the distribution law. This one multiply to the first term, C0 e to the power omega. There's no derivative. And then this term multiply this term. Okay? And my goal is to find out what is C0. Up to here, is that okay? Spend quite a lot of time on this to repeat. Okay, so now I'm going to apply the bra on left. What is the meaning of applying bra on left from linear algebra's term? You try to do what operation? These are all cat, right? I try to apply the bra on left. What I'm trying to do? Inner product. I try to find the inner product of this big term on 0. So I try to project this state to 0. to find how much component it has on the zero basis state, right? So I apply the inner product, then what will happen? Then I look at the left-hand side again. When I apply the inner product, all of them are just scalar, so I can just go in, right? When I say I just go in, I mean this. Apply the bra of 0 from left. This is a scalar. I take it out, take it out, take it out until I meet the cap. Right? So it's just like row vector. Multiply scalar. I move to the right until I meet the column vector. And that is 0, 0. Okay? So I do the same thing for the second term, right? Because I multiply from left, I have this distribution law. This is just an addition, so I have distribution law. So I continue to do this for the next term. I also get 0, 0. Okay? Then I continue, because I have four terms, right? For this left-hand side, 1, 2, 3, 4, they're addition, right? Then I'm lazy, I'm not going to write this term, just let me save the time. I will get 0, 1 for this one. And then I will get 0, 1 for the fourth one. Any questions of what I'm doing here? Any questions? Is this clear? Right? I multiply from left. This is just a linear, right? Addition. So I applied 0 to each of these terms, right? I'm very slow, but in the future, it's so clear to you. You will just say, okay, go to here, right? What is 0 inner product 0? Someone say 1, right? Because it's orthonormal. What is 0, 1? 0, right? Again, I remind you, the so-called 0 is spin up. 1 is spin down. They are orthonormal, right? When the qubit spin down, it doesn't have any component that is spin up, right? When it spin up, it doesn't have any component that is spin. So because of this, this can be simplified to I h bar and C0 dot e to the power I omega LT divided by 2 plus, because it is 1, I don't need to write it anymore. Omega L divided by 2 e to I omega LT divided by 2. Right? What I'm doing is just, this is 0, this is 0, this is 1, this is 1, so I only have this left over. Is that okay? Okay, so, I mean, when you're very familiar to this, you don't need to spend so much time. You already see that 0 come in, this term will be kept, this one term will be kept, this term is gone, this term is gone. Right? So you need to be familiar with this. Then of course the next step is they are equations. So I apply this to the right hand side, I need to apply this to the left hand side. Now I need to apply this to the right hand side also to make it balance, right? So I'm going to apply it to the right hand side. So for right hand side, what do I have? Maybe I use the last page so it is easier for you to see. I was planning to do other things. So I apply this to the right hand side. Then what is this? This is the right hand side. So I'm going to apply 0 to the left. Can I keep moving this 0 all the way so that I see the 0 cap? No. Why? Huh? You have operator. Right? If you don't know, you just think about matrix. This is a row vector. This is a matrix. This is a matrix. This is a column vector. Of course, I cannot swap them. They do not commute. It doesn't make sense, right? So this time I got stuck. I only have this. But I have the rights to move this scalar to the left. Okay, so what I get is C0 e to the power I omega L divided by 2t. And then I have this term, 0 H0 0 plus 0 Hi 0. This is the first term I got. Then I also have the second one, right, which is 0 H0 1 plus 0 H not HI 1. Do you see this? I apply to here. I have not done any operation. Scalar, I take it out, and I just do 0. It's just a multiplication, right? 0 bra times H0 times 0 cat plus 0 bra times HI times 0 cat. And do the same thing. 0 bra times H0 times 1 cat, and then 0 bra times HI times 0 cat. Is that okay? So this is a mess. But if you go through carefully, you will find that you naturally will achieve the same thing as I have done, because you understand that you cannot swap the row vector and the matrix, right? They don't commute. You cannot just swap them, right? So you get this. Now then the question is, I need to know what it is 0H0, 0HI0, right? What are these? Do you remember what are these that we discussed earlier? Is what? Expectation. Yes. But here it's not expectation because you have two different elements, right? But this is the element of the H matrix. You find the matrix, right? So let me just recall. I discussed this already, right? H0J is the element. No. Is the I row, J column element of H0. Remember this? That's how you find in the basis of IJ, right? In the given basis. Okay, but that's not important. This is just to remind you. What we really want is to find out, that's okay, just recall, to find out what they are, okay? So, what is 0H00? The point is that we need to find out what is H, right? And we found that already. What is H0? Negative B0 H bar E divided by 2M sigma Z. Or, I should have also write this clearly. This is also equals to negative H bar omega L divided by 2 sigma Z. You can prove that, okay? I jump a little bit. Just based on this equation, you can prove that, okay? So this one is just equal to negative H bar omega L divided by 2 sigma Z 0. Maybe you forgot the equation, but does this make sense to you? If I were a student, I might get confused. But any question about this? You need to ask. Is this straightforward to you that I substitute H0 as this? Or something wrong? You think something doesn't make sense? Given that I told you that H0 equal to this. Right? It's okay? Just let me know anytime, right? You need to make sense out of this. So because of this, this is just equal to negative H bar omega L divided by 2, 0, sigma 0, right? How are you going to evaluate this one? What will you do when you see this? You probably will get panicked if you are not familiar with it, right? what will you do? What will you substitute? Put in what value? The vector, the matrix, right? You can just put in the matrix. What is the value of 0 for row vector? How do you represent 0? 1, 0. What is sigma z? 1, 0, 0 negative. Yeah, you need to memorize this, right? What is 0 cat? 1, 0, right? Go through the calculation. You see that this is just equal to 1, 1, negative h bar omega L over 2. Hey, but you will see that, hey, I knew that already. This is the eigenvalue, E0, right? Why? Because as you just said, this is calculating the expectation value of state 0. And then, of course, the energy of state 0 is equals to negative h bar omega L because it has the energy of E0, right? So here, just repeat what we already know. Is that clear? Yeah? So similarly, of course, you know that 1h0, 1 equals to what? Is calculating the expectation value, the expector or the eigenenergy of state 1. What should that be? What should that be? Positive. Thank you. Positive h bar omega L over 2, right? You can go through the same derivation. Okay, good. Oh, but we don't need that, sorry. This is for another part, right? Because we are not calculating 1h01, right? We don't have this. It's all 0 from the left. So we don't need this. What we need is, what is 0h01? Oh, someone say 0. Why? Yeah, very good. Say H0 does not change one vector because 1 is the eigenvector of H0. Right? So you will get something like H0, E1, because it's the eigenvector, then give me E1, 0. So this is a good way to understand, very good. Or it doesn't have off-diagonal element. Or you just plug in this equation, but instead replace this by 0, 1. You will get 0. Okay? So basically what you say is what? There's no coupling between the two states through H0, right? So the original Hamiltonian H0 does not couple 0 to 1. Basically, it means whatever state you have, you put into this Hamiltonian, 0, the one state will not transfer to 0, and 0 won't transfer to 1, vice versa. Okay? But what interesting is this one. Let's look at this. How about 0 Hi? Right? So this is different. So let's just write down the Hamiltonian of Hi. This is equals to, you can copy from earlier. Here, right, on the bottom, Hi is this. Now, so I'm going to put EH bar divided by 2m, B1 cosine omega 1, very long, but they are all scalar. Okay? Except that I have sigma x. Right? So I can take this out. This is 1, sorry. Right? So let's consider 0, 1, sigma x. What is this? Right? Let's just try, go through the matrix. This is 1, 0 because it's 0. And what is the matrix for sigma x? 0, 1, 1, 0. And then what is the vector for 1? 0, 1, right? You go through the math. This is 1, 0, 1. Sigma x couples 0 to 1 because it has off-diagonal elements. So it means that it's going to change the state of 1 to 0 as a function of time. They will oscillate back and forth. So because of this, then we have 0 Hi 1 equals to E h bar divided by 2m b1 cosine omega 1t. And similarly, 0 hi 0 give us 0. Because while it couple 1 to 0, it doesn't couple itself in that sense. Is that okay? This one, please go through the math and trust me, right? So coupling. So here we say coupling. Okay, good. Where am I now? Now this is page 8. Okay, so then let's continue. Because of this, I just show you. This is the left-hand side after we do the inner product, which is this part. And this is the right-hand side, okay? So from 3, which is actually from 4 and 3, from 4 and 3, right? So this is part 5. From 4 and 3, what is the left-hand side? Right, I'm going to do the left-hand side. Is going to be what? I h bar C0 dot e to the power I omega L divided by T plus C0 I omega L divided by 2 e to the power I omega L divided by 2T, right? Just copying, right? This is very complicated, but what I'm trying to do is just copying it faithfully. On the right-hand side, we already know what? This one is going to be what? H bar, negative H bar omega L divided by 2, right? Negative H bar omega L divided by 2. This one is what? 0 because no coupling. I also know this one is 0 and this one is EH bar, yeah, you can say 1 EH bar divided by B1, I think is what? 2m? 2m times cosine omega 1t, right? So I'm going to write this down as cosine e to the power I omega L divided by 2t times negative h bar omega L divided by 2 plus C1 e to the power negative I omega L divided by 2t times, very long, E h bar divided by 2m b1 cosine omega 1t. Sorry, this is difficult to see. Let me just start a new line. E to the power h bar b1 divided by 2m cosine omega 1t. Right, let me check my cheat sheet. Any questions? And here there's something I can cancel. If you look at this carefully, this term and this term can get cancelled. Why? because this is I h bar. If it goes in, I times I is -1, and then omega h bar omega L divided by 2. And this is negative h bar omega L divided by 2. Both have C0, both have e to the power I omega t divided by 2t, right? So these two terms got cancelled. So as a result, I have I h bar C0 dot e to the power I omega L divided by 2 equals to C1 e to the power h bar B1 divided by 2m cosine omega 1t e to the power negative I omega L divided by 2t, right? I would suggest you not try to copy, but try to answer. And then the rest are just math. I'm going to just, what I'm going to do is going to move this IH bar omega, or I keep IH bar on the left or no? Okay, I'm going to keep I on the left and then move this E term to the other side, right? So what do I get? Because I keep I on the left, then I have I C0 dot equals to C1 EB1 divided by 2m cosine omega 1t and e to the power negative I omega LT, because this is negative 1 over 2, this is 1 over 2, so I put here, it becomes omega L2, LT. Let me double check. Is there any questions? Yeah. No, it's just the way I do it. You don't need to keep it. Yeah. Yeah. So I emphasize so that you see that you don't think that is a typo. Now, you don't need to worry about the math again, right? The important thing is how we arrive this step. And what is the result? It tells us the rate of change of C0, the rate of change of 0, which is the coefficient of the 0 state, is proportional to C1, which is the coefficient of the one state, and the magnetic field. If you didn't have this oscillating magnetic field, the rate of change of C0 is not going to depend on what you have in the one state. So there will be no oscillation. You will start seeing the oscillation now, right? Because if I have a large C1, it means my C0 will increase very fast. If I have a small C1, my C0 would not increase, right? Because this is dC0 dt. So you can say if I have lots of C1, then I start increasing C0. But their magnitude need to add to be 1, right? The square of their magnitude. Then it means that I am just transferring the component of 1 to 0, and then 0 to 1 back and forth. Right here, I need to show that from C1 to C0, right? So similarly, so this is something you need to try yourself in your assignment. I can apply this one in step, which step? I think is 3, right? In step 4. In step 4. Right, I can apply this in step 4, then what I will get? You will get something very similar, but this time it is IC1 dot equals to C0 EB1 divided by 2m cosine omega one t e to the power I omega LT, right? One of them is omega 1, one of them is omega L. You need to be careful. I have these two equations. Is this okay? Let's do not think about math now. I know this is confusing. You need to go back to chart, right? But what do we get now? Again, I say that the rates of change of C0, remember what is C0? Let's go back. C0 is the coefficient in front of 0 state. C1 is the coefficient in front of the 1 state. If I have a large C0, it means I have more component pointing up. If I have a large C1, I have more component pointing down. If all of them are C0 is 1, C1 is 0, then it means it's just spin up. When it is all C1 is 1, C0 is 0, then you only have spin down, correct? And these two equations tell me that my C0 will change very fast, will increase very fast if you have a large C1. And this equation said my C1 will increase very fast if you have a large C0. In order to make sense out of this, and in order to keep C0 squared plus C1 squared equal to 1, because of the normalization requirement, in order to do that, then you basically say that your C1 must decrease and you will have a lot of C0, right? And then once your C0 has a lot, you have a lot of C0, then C1 will increase back. This is the only way to satisfy this equation, right? Do you agree? And isn't that is an oscillation? Your qubit state will oscillate from a lot of component of spinning down to spin up, and then from spin up to spin down. Because when you get everything in the spin up, let's say C1 is 1, then your C0 will increase. And because at that time C0 is 0, your C1 is not going to increase, right? So this completely agree with what we are thinking. And the rest is just equation. Okay? Questions? Okay, right, so understanding this, so these are the two equations we just said. Now we will introduce a concept called rotating wave approximation. Let's look at this equation, right? I can actually, for this cosine omega t, if you forgot, cosine omega 1t is equals to e to the power I omega 1t plus, sorry, maybe let me just use, I don't have space, use a general one, right? I want to express cosine theta in terms of exponential. Cosine theta equals to e to the power I theta plus e to the power I negative I theta divided by 2. Okay, you can go back to substitute the equation to prove this. So this one equals to what? This one just equals to E divided by 2m and then B1 and then e to the power I omega 1t plus e to the power I negative I omega 1t divided by 2 times negative I omega LT times C1. Right? I'm just copying everything except that I substitute cosine omega 1t into the summation of 2 exponent divided by 2. Is this okay? I just substitute this one. Now, why do I want to do that? Because I split it into 2 components. This becomes EB1 divided by 4m. And the first term is e to the power I omega 1 minus omega LT. Then I have a second term, which is e to the power negative I omega 1 plus omega LT times C1. Do you agree? Now, if omega 1 and omega L are very close to each other, right? Again, what is omega L? Lamarck frequency is how fast the qubit presets due to the DC magnetic field. What is omega 1? Do you remember? Omega 1 is how fast this magnetic field oscillates. If they are very close to each other, basically it's saying that when it is precessing, your magnetic field's relationship to it is tracking it. Think about if they are exactly the same. Then when the qubit is in this place, maybe this one is, or just extreme case. Let's say qubit is here, and then your magnetic field may be pointing here, the x direction. Then you're pointing at the qubit, right? If they have the same frequency, after half cycle, the qubit will go to the negative side. Your magnetic field will be again pointing at the qubit because you have the same frequency. And if you go back to full circle, you come back to the original position, your magnetic field will be pointing at you again, right? So you see this enhancement, right? So here, or what? But there is another thing, right? But here what I'm trying to say is, omega L minus omega 1, which we call the detuning delta, you will see very frequently in different quantum mechanical problems. We assume that, actually I want to go directly. Let's just assume, no, don't do this yet. Then this one is approximately equal to e to the power b over 4m, e to the power negative I delta t times C1. Because this term has a very large frequency, this term, its contribution to the problem can be FH out. Okay, so think about, let's say I stand here, right? If someone try to push me from the left, I will fall to the right. Someone push me from the right, I will fall to the left. But the time for me to fall to the right has certain constant, let's say in the order of 1 second. If that guy push me every 10 seconds, then when he pushed me one time, I already fell on the floor before the second time he tried to push me, right? But let's say he's doing this very fast. He pushed me from left and right in the order of 0.1 second. Before I was able to fall to the left, he pushed me from the right again. And before I can fall to the right again, he pushed me from the left again. Because its frequency is much higher than my frequency to fall, in that sense, right? So the effect of the periodic action on me can be canceled out in the time scale that I'm interested in. So that's why this term can be ignored. Okay? By ignoring the high frequency term e to the power negative I omega 1 plus omega L, because they all have high frequency. Or omega L, where we should say omega 1 plus omega L is much larger than omega L minus omega 1, right? The sum is much larger than the difference. This is something the first time we encounter. Later we will see why it is called so. This is the so-called rotating wave approximation. Okay, we ignore the high frequency term. But why is it called rotating wave? Later we will see it from a more graphical perspective. But from mathematical perspective and from the time scale perspective, I hope that I explained to you. Right? Someone periodically try to push me left and right. If he does it really fast, I will not feel the effect because it has an even force from both sides. Although not apply at the same time, but apply at the time scale that is very fast before I can respond. Right? Make sense? Any questions? Right, so then I have this one, right? Now, then I want to introduce another concept. Right, this is, yes.
Should it be omega L minus omega 1 equals to minus delta?
No, so you see that I define omega L minus omega 1 equal to delta. So this one becomes negative I delta T. Okay, I swap them. Do you see that? So this is equal to negative I omega L minus omega 1, right? Do I answer your question?
Oh, yeah, I see now this one.
Yeah, I swap it. Yeah, a little bit confusing. Yeah. So this is called rotating wave approximation. Now, then there's a situation. If I make delta equal to 0, this is called spin resonance. So what does it mean? You will see better in the block diagram, but the result is this. Then you have I C0 dot equals to EB1 over 4MC1. Because now e to the power I delta is 1, right? Because delta is 0. Delta times t. This is not delta t, this is delta times t, right? So this is 0, this is 1. So now I have EB1 divided by 4MC1. And why it's called resonance? I already told you. If the normal precessing frequency is the same as the oscillating magnetic field, the magnetic field just keep tracking the motion of the qubit state. Right? Not motion, but they resonant. They have the same frequency. It's just like real resonant interference. Right? Whenever you are in the x direction, I'm pointing at you. When you go to negative, I'm pointing at you. You are right, because they all oscillating at the same rotation frequency. So that's resonant, like the bridge, right? When the bridge vibrates, you try to step it with the same force, you have the resonance. And this resonance will cause the flipping of the qubit, which is rapid oscillation. But we are not there yet. So this is the final simple equation. So I call this 1, 2. You do the same thing. Similarly, right? If you apply rotating wave approximation, and then apply spin resonance condition, right? Rotating wave approximation plus delta equal to 0. You get I C1 dot equals to EB1 divided by 4M C0. This is another equation. So we did not do much, right? We only just simplify these two equations, but there are lots of physics here in this simplification process. Rotating wave approximation and spin resonance. Okay? Any questions? So lots of math, I know that, but you don't need to remember, but you need to, yeah. Can we what?
Can you actually make the frequency?
Yes. Yeah. So that is spin resonance actually came from nuclear magnetic resonance. That's how they do the MRI. But they use the nuclear spin. They do it in the right frequency, and then different atom is going to react differently because they have different spin and different gyromagnetic ratio. The G is very different. Then that's why you can map out all those problematic cell or whatever by MRI. So all this came from magnetic nuclear resonance. Yeah. I mean that you always have a night wave, right? So, but you can match exactly. But you can tune, right? Just like you use radio. I don't know, you guys too young, maybe you don't use radio, right? When you tune it, you always can just keep tuning. Eventually you have the right frequency, then you can hear that. right? And you off a little bit, you will still hear a little bit, right? But then it means it's not clear, the picture, right, in that domain. Okay? Good. So again, do not worry about this math. You just need to know what I'm doing. Then what I can do is I can plug in this equation to this equation to solve it, right? Because I have C0 and C1 and C1 and C0, right? And don't know, I actually skipped some step. So for example, I will start with, first I have I C0 dot equals to EB1 divided by 4MC1, right? Then I do one more time derivative. Do you see that? I just do one more derivative, right? So I have 2 dot now, dot dot, second derivative. And on the right side, I have 1 derivative, right? So that I can plug in C1 dot into it, okay? Which will give me EB1 divided by 4M divided times EB1 divided by 4M I C0, right? Because here you see that if I want to get C1 dot, I need to divide I to here, right? So I just plug in this C1 dot. So yeah, so I did not do a good job. Then the I can got cancelled. This becomes C1 dot dot second derivative plus EB1 divided by 4M square C0 equal to 0. So I have a equation of motion for C0. We call it equation of motion. You have people from physics, you have people from EE. What is this equation? I mean, have you seen something similar before? Yeah? This is the, for E student, LC tank, right? Maybe voltage dot dot equals to something times plus voltage. This one is the resonance frequency, right? And, or, yeah. Is this also the wave equation? I assume, right? I forgot. Yeah? So, you naturally will say, let me define something. Define omega R dash is omega R dash. It's still not the Rabi frequency. EB1 divided by 4M. Okay? Then I have this equation. C0 dot dot plus omega R dash square C0 equal to 0. Right? If you're not familiar with this, just remind you this is the second derivative of C0 plus omega R dash C0 equal to 0. This is the wave equation. Okay, it tells us how C0 evolved as a function of time. Then go back to your differential equation. Don't worry if you forgot, because I forgot also. All you need to know that the solution is C0 equals to general solution, C0A cosine omega R dash T plus B sine omega R dash T. The solution to this second order differential equation is this, right? This class is not about differential equation. I won't ask you to solve it, right, in even assignment. You just need to trust me, this is the solution, right? But you should know that why we came up with this, okay? And you should know the feature. So how about C1 then? You may think that this is difficult, but we already know the relationship between C1 and C0 from these two equations, right? So I just give you the answer. CIA sine omega R dash T plus IB cosine omega R dash T. And here again, it confirms what I told you earlier. It's an oscillating problem. C0 will go to very small and then go up. They all follow this trigonometry equation, right? Sine, cosine, formula. Is this okay? Then what do you want to do now at this step? You have the solution, but do you have everything already? You already understand the problem already? You got the answer, how the qubit will evolve already, or not yet? You still don't know what is A and B, right? Because you plug in this to your qubit, you still need to find out what is A and B. So here we are going to do this. Okay? What? Okay, so I just write it again. C0 is this. C1 is this. And this is the state of your qubit under this complicated system. Vertical electric field pointing down and oscillating electric field in the x direction. This is the state. We already found what is C0 and C1. But the problem is that I need to find A and B. If I can find A and B, I plug in, I'm done, right? So how do I find A? So what I can do is to find at t equals 0. At t equals 0, what is C0? At t equals 0, what is C0? A, thank you. Because sine omega t equals 0, cosine omega t equals 1. So at time equals 0, 0, this is A, right? But what is the qubit state at time equal to 0? Let's recall. The qubit state at time equals 0 is just in general the cosine theta over 2 e to the power negative I phi, I call it initial angle with this, plus sine, what is that? Anyone can tell me? Theta over 2 e to the power I phi 0 divided by 2, 1, right? This is just to recall, right, what we learned earlier. Am I right? Any state, before you solve the problem, you must have an initial state. And that initial state, I just call it, name it to have a theta equal to theta naught and phi equal to phi naught. Because it must have a certain polar angle, certain azimuthal angle, right? So this tells us that A equals to cosine theta 0 over 2, theta naught over 2 e to the power negative I phi naught over 2. Okay? Now, how about C1 when time equal to 0? Based on what we see here, when time equal to 0, C1 equal to IB. Right? Because cosine 0 is 1, sine 0 is 0, so I only have IB at time equal to 0. And at time equal to 0, this is equal to sine theta 0 over 2 e to the power I phi naught over 2. Right? So, just plug in, then you are done. Right? You can write a program already to see how the state will evolve as a function of time. But this is pretty complicated. Okay? Which is fine. So let's look at a special case. Okay? Look at a special case. So that we can understand better. What is this special case? It is the case when phi not equal to negative pi over 2. It means that this state was negative pi over 2. Can you tell me where is negative pi over 2 for phi naught? If this is along this circle, along this line, this is 0. Here is pi over 2. Here is negative pi over 2. Basically saying that if my initial state is along this circle, then there's something interesting I can see. Something easy I can see. That's it. That is the special case. Is this okay? The meaning of negative pi over 2? right? So we're looking at this special case that it equals to negative pi over 2. So with that, then y, so I will look at C0 again. C0 equals to A cosine omega r dash t plus B sine omega r dash t, right? This was given already. We solved it. But now I'm going to plug in everything. I know that this is equals to, I'm going to plug in, right? What is A? Cosine theta 0 naught over 2 e to the power negative I phi naught over 2. And then I'm going to multiply this by cosine omega r dash t. And then B is actually negative I. The reason is IB equal to this, IB equal to this. So B is equal to this divided by I. So I got negative I. Right. Sine theta 0 over 2 e to the power I phi naught over 2. Okay? But this one is just equal to e to the power I negative I pi over 2 for this one. Okay? Now, because the rest of the math, so I will go a little bit faster. So I'm going to do is to just go ahead, run it, and show you the result, right? I'm going to take out e to the power negative I phi naught over 2. But what is this? E to the power I phi naught over 2. Maybe I should have done that earlier. If phi naught equal to pi over 2. No, sorry, I cannot do that. Yeah, let's keep this. I jump a little bit. Then this is cosine theta 0 over 2. I just take out the phi naught over 2, right? So what I did is I take this out, e to the power I phi naught over 2. I factorize this, then I have cosine theta naught over 2, cosine omega r dash 2, right? And this is minus sine phi naught over 2 e to the power I pi over 2 plus phi naught over 2. Why is that? Because I have negative I. I is e to the power negative I pi over 2. So I combine these two together, but actually this one, so I jump 2 steps, right? So this one I factorize e to the power negative I phi naught over 2. So this one need to becomes e to the power I phi naught, right? Because this is negative something over 2. This is plus something over 2. I factorize this negative over 2, then this is gone, but this one need to be without over 2. Right? So that's why I have phi naught. And this I is this. And now you can see this special case because this is equals to negative pi over 2. So this gives me 0. Right? That's why I say this is a special case. With this, I think I'm missing the cosine omega. Right? I also have to write down the, I miss this whole term, sine omega r dash t. So this is sine omega r dash t. This just use the trigonometry equation. You see this is e to the power negative I phi naught over 2 times cosine theta 0 divided by 2 plus omega r dash t. Is this okay? Maybe not, right? What I'm doing is cosine A cosine B minus sine A sine B equals to cosine A plus B. Again, I don't expect you to memorize it. No need to write this in cheat sheet either. But I'm using this equation, right? So let me finally just write down the form. I think this is okay, right? And then for this, it's enough for you to do the assignment already. You can start typing.